So the solutions to the midterms are uploaded on Carmen. You can check the solution, you can check whatever you have written, and then if you have any questions, please feel free to reach out to me. Today we'll continue our discussion on approximate dynamic programming, and in particular we want to talk about not limited lookahead, but lookahead approximation. So I want to minimize Ct plus 1 plus summation t equals 0 to capital T Ct xt ut. This is over all policies phi t that maps xt to ut, and I have the constraint gt of xt ut less than equal to 0 and xt plus 1 equals to ft xt ut, and I am going to assume throughout this lecture that capital T, which is the terminal time, is much larger than 0. Okay, this is the case in most of the applications. You want to send a rocket to Mars. The rocket is going to reach there in maybe like 6 months or 1 year, but it needs to make a decision every 100 milliseconds. So you can imagine the number of time steps capital T you need to have in order to make sure that you're able to control the rocket reliably so that it reaches Mars eventually. I'm being a bit sloppy here, but this is a function of xt plus 1. And the question I had posed to you is, given that we have such a long time horizon, how exactly should we go about figuring out an approximately optimal solution to this particular problem? So what do you think? I have to send something to Mars. My capital T is of the order of 1 billion or 1 trillion, something along those lines. How should I go about solving the problem? Yeah.
So you want the final time to be like 1 billion steps ahead, but nothing's going to change fast enough for there to be like catastrophic veering off of course. So you could maybe look ahead like the first couple hundred steps or.
Okay. So you want to look ahead maybe 100 time steps or 200 time steps. Okay. So should I do the following? At every point of time, I am going to do the minimization of summation Cs, xs us, s goes from t to t plus 100, right? That's what we want to minimize. Okay. So my running cost is I want to minimize the amount of fuel because that's a lot of weight on the vehicle, on the rocket. So I want to minimize the amount of fuel. So I want to control it in a way that the total fuel consumption is minimized. My terminal cost is I should be at a specific point on Mars. Okay. So this is my fuel cost and this is my terminal cost, which is I'm at a specific point in Mars. If I'm minimizing the fuel cost over the next 100 time horizon, what exactly is the action I should be taking? If I'm only minimizing the fuel cost?
No fuel burn.
No fuel burn? That's going to be the optimal solution. What happens if I don't burn any fuel?
You might not stay perfectly on course.
No, actually you won't even start, because from the very beginning at time t equals to 0 you are at the ground. You're solving for 100 time steps and you're not burning any fuel. You will be at the ground.
I was assuming you were already moving to get
Right. So how should we correct for this particular behavior? The intuition is correct. We should only be solving for the next 100 time steps, next 10 seconds, next 15 seconds. But then what is missing here? Yeah, what is missing?
Could we add like a reward for speed? Like if we're going a certain speed, then we're rewarded. So then there's
So you want to add additional reward?
something like that. Because otherwise, there's no incentive to start.
Okay. So you want to add an incentive to start. Okay. But how are you going to direct the rocket towards Mars?
Well, when you're on the ground, it's kind of like it's over that way. So start that way. But
Okay. So we need to put an incentive to get to the Mars, get to the planet, or get to the point where we want to go to. How do we put that incentive? So what is the incentive here to get to the Mars? The incentive is the terminal cost, right? The terminal cost is allowing us to create an incentive that we need to get to Mars, no matter how much fuel you need to burn. I mean, of course, we want to optimize the fuel burn, but no matter how much fuel you need to burn, you still have to get to Mars because that's what the terminal cost is asking you to do. So what we need to do is, instead of this, what I'm going to do is I'm going to add a terminal cost here. I'm going to add a terminal cost here, which is going to make sure that I'm on path to get to Mars. And the reason why I write v tilde is because this is going to be an approximation of the true value function. So if I write the value, if I write the one-step dynamic program, I actually am trying to minimize this is what I'm trying to minimize. This is of course subject to the constraint gt less than equal to 0. So all I'm going to do is, in order to have a look-ahead approximation, all I'm going to do is replace this value function, which is the true value function, which comes from solving this complicated dynamic programming problem. I'm going to replace it by an approximation of Vt plus 1. And if I want to have a much longer look-ahead policy, I'm going to replace it by V tilde t plus 100. Okay, so roughly the kind of algorithms we are going to talk about today, they'll fall into two different categories. One is model predictive control, and the other one is going to be this kind of algorithm, which is called rollout algorithm. Okay, so let's talk about the two classes of algorithms. Any questions so far? I'm going to erase this side of the board. So in model predictive control, what we generally do is, based on some heuristic, we figure out a trajectory x bar k that we need to track. So if I have to go to Mars, I have to go, I don't know, to stratosphere, then I have to go to the outer space, then I have to take a couple of rounds of Earth, then I need to get to the moon, and then from there I will get to Venus, and then from Venus I'll get to Mars. Okay, that's the typical trajectory. So you first go inside the solar system, and then you tend to go outside of the solar system. So some physicists sat down in 1960s and figured out that, okay, the way to get to Mars is to do like these kind of maneuvers and then get to Mars, and that's going to save us a lot of fuel. And he or she used a lot of physics and astronomy and a lot of other phenomena that physicists study, and they figured out that this seems to be the best way to get to Mars. So they derived this x bar t that needs to be dragged. Okay, does that make sense? Okay, so we used physics, we used biology, we used chemistry, we used our intuition, we used our tribal knowledge, whatever knowledge is needed in order to derive a trajectory that we will be tracking. And then what I am going to do is minimize. So at every point of time, so at time t, I will solve this tracking problem, minimize summation Ct of xt ut t equals to, sorry, s. I need to use, we have not used s, right? So I'm going to use s. S equals to t plus tau. I'm minimizing over all pi s. And then I'll have the usual gs xs us less than equal to 0. And then I'm going to say that xt plus tau equals to x bar t plus tau. So I'm going to add this terminal constraint to my problem. Okay, so that's one way to solve it. The other way to solve it is you create a tracking, you change the cost function itself. So instead of trying to minimize the cost, you are basically minimizing the tracking error. And this x bar of t is what you are trying to track, but you kind of make sure that x bar of t tends to minimize this particular cost. Okay, so like I said, if you want to go to Mars and if you want to do this dynamic program, remember that you need to run dynamic program over the entire state space. What's the state space when we are going to Mars? Well, it's the entire space, right? So we can't really run a dynamic program over the entire space because that's a very, very large set. So somebody needs to come up, somebody needs to narrow down the amount, the kind of space that we are looking at. And the way to do that is to come up with this x bar t, which kind of minimizes this particular function. But the way to make the minute to minute decision or second to second decision is by solving either this problem or you can solve this problem. xs minus x bar s transpose q, xs minus x bar s plus u transpose ru such that gs less than equal to 0, xt plus tau equals to x bar t plus tau, s equals to t2 t plus tau. So that's roughly another way to do it. What do we have to be careful about in this formulation? What can go wrong if I'm trying to solve this problem? So in this case, I've assumed that this x bar of s is kind of close to the optimal trajectory. Potentially you can use you can use the Pontryagin minimum principle to compute what this x bar of s is going to look like, and then you're running dynamic program in order to solve this problem. So the question now is, what can go wrong in this formulation? Yes?
It might not reach that terminal state every time.
Yeah, wonderful. So this particular constraint can lead to infeasibility. Okay, because there are some errors that are happening in the environment. There is like crosswind, there is some random stuff happening, there is maybe birds flying into the rocket or something like that. So this particular constraint may be very hard to meet because of that reason. So how do you solve for that if this particular constraint is difficult to meet? What would you do?
You make some kind of incentive to get close to that constraint.
Right. So we can basically just add this some lambda of xt plus tau transpose a, well, let's remove the lambda, qt plus tau. Sorry, I should have this x bar t plus tau here. So you add this terminal cost function to this particular constraint. So you erase this particular equality constraint here and you add it as a additional cost function to this particular problem. So this is known as a soft constraint. This is a soft constraint and this is a hard constraint. So you can remove the hard constraint and you can create a soft constraint, and that way you can try to solve the problem. And that's why we studied the linear quadratic problem, because linear quadratic problem kind of appears in these kind of situations. So what we have done in this particular formulation is we started with this particular problem. It was very difficult to solve. So what we did was, because the bulk of the cost was actually the terminal cost here, so instead of having this bulk cost at the terminal time step, we actually converted it into a running cost, and now we are trying to minimize a subset of that running cost with some constraint by massaging the constraints or by adding the soft constraint in the cost function itself. You've tried to simplify the problem that you were trying to solve. Now maybe if you solve this problem, the total fuel consumption will be like 4,500 ton, and instead if you use this particular algorithm, your total fuel consumption will be 4,700 tons. You're not optimal, but you are still close to the optimal, and that's the idea behind Lookahead approximation. Any question? So where do we use these kind of algorithms? So vehicles use these kind of algorithms to go from point A to point B. So they always want to, they use MPC. So people in Center for Automotive Research use MPC day in, day out. Like half the PhD thesis is in MPC algorithms for different activities. Then if you're a trucking company and you need to move a lot of trucks all the way from East Coast to West Coast and West Coast to East Coast, moving things from one point to another, you also have to solve problems of this type because ultimately you want to make sure that over a year you are optimal, but because you can't really solve for an entire year, especially because there is so much uncertainty over the entire year, you tend to solve the problem for like 2 days at a time or 3 days at a time with some sort of terminal cost, keeping the constraints of truck drivers in mind that after 3 days I want to be at my home, and so that's the constraint they need to work under. Same thing with airline staff as well. So airline staff also needs to be home every few hours or every few days, and so they also keep that into mind when they are solving this problem. So of course airlines also need to schedule over several days or over several months, but they can't really solve that problem, so therefore they need to solve problems of this type in order to optimize the total cost and make sure that all the constraints are met. And the constraints typically in these problems is that air hostesses want to reach their home on a specific date and time, or alternatively truck drivers have to reach home at a specific date and time. Sometimes there are also constraints, like for instance in the case of pilots, they can't really fly for 8 hours at a stretch, so then they need to have some rest time and downtime and so on and so forth. So all those constraints are also there. So airline scheduling is actually a very difficult problem. So if you ever encounter those problems, there is a lot of constraints that you need to keep in mind. So that ends our discussion on model predictive control. Now I want to talk about rollout algorithm. Any questions on this? No? So if the hard constraint is infeasible, you basically put a soft constraint. Okay. So less well known, but rollout algorithm is actually a very important class of algorithms. Much of the field of reinforcement learning actually starts from this particular algorithm, rollout algorithm. So what's the idea in rollout algorithm? The idea is as follows. So remember, we need to, okay, so let me write down the expression. Minimize pi s summation cs s equals to t plus tau plus v t plus tau plus 1. I want to minimize this, and it's going to give me a true solution. So I'm going to get pi star t to t plus tau. Oops. Right, so all of you agree that this is going to give me pi star t plus tau, okay? So this is like the optimal policy at time t, t plus 1, t plus 2, all the way up to t plus tau. Now the biggest problem in using dynamic programming is that computing this is very time consuming. So how should I go about solving this problem? So there is a value function that I need to keep track of, and I don't quite know the value function. In fact, the value function, computing this is very, very difficult. It's very time consuming because I have to solve this particular problem at all time steps, and as we've mentioned, capital T is very, very large. So what do we do in this particular scenario? What we do is we pick a policy. Let me call this pi tilde t to capital T. So I have some policy, okay? So this policy is a heuristic. This is known as a base heuristic. So I pick a base heuristic policy. This policy is supposed to meet all the requirements, constraints, and so on. So for instance, you want to solve a specific problem, but instead you pick the PID controller as the base heuristic because that's the controller that has been used since the last 50 years on that particular machine. So you pick a policy, that's a base heuristic, and then you evaluate the value function as follows. V tilde t plus tau plus 1 x t plus tau plus 1 equals to summation cs xs and pi tilde s xs plus ct plus 1 xt plus 1, and s goes from t plus tau plus 1 to capital T. So I'm basically evaluating the cost until the terminal time step under the base heuristic. So this is the total cost. Under base heuristic. So I pick a base heuristic policy. I evaluate so I pick points in the space xt plus tau plus 1. So in this space, I pick a bunch of points, and I I compute the total cost starting from that particular state all the way up to the end of the horizon, and I store it in this value function v tilde. Okay, and I can use some interpolation. I can use some function approximation in order to come up with this function v tilde. Okay, and I'm going to replace this function v here with v tilde. So I start with the base heuristic, I compute the total cost to go, and then I replace the terminal value function with this cost to go function. And that's called a rollout algorithm. Okay. Now, of course, I have picked one base heuristic, but you can pick multiple base heuristic. So you go around the room and you ask, okay, what's your base heuristic? What's your base heuristic? What's your base heuristic? You get 3 different base heuristics. You compute the cost to go under the 3 different base heuristic and pick the minimum of the cost, store it in v tilde. Okay, so you can always do that as well. If you have multiple base heuristics, you take the total cost and then take the minimum of the total cost and store it in the value function. So you can accommodate any number of base heuristics as you want. Okay, typically the base heuristic is what you have already been using so far, something that's been used for several years. So you use the same base heuristic and then you compute the cost to go. Then you plug it in here. So this becomes v tilde. Sorry, let me write it somewhere else. So then you minimize summation ct plus v tilde t plus tau plus 1, and this is called the rollout algorithm, CS, and then GS less than equal to 0. This is known as the rollout algorithm. This problem of infeasibility doesn't arise in the case of rollout algorithm, because remember, we are not putting any constraint on the terminal state of this particular optimization problem. Any question on this? How many of you have heard of the term reinforcement learning? Okay, many of you. So I know, for others who have not studied reinforcement learning, you can maybe listen to it, but it wouldn't make much sense. So what generally happens in reinforcement learning is you have a simulation system which is simulating the state transition function, and then based on the simulation, you come up with a policy pi tilde, and so first you do the first round of reinforcement learning and you get a first base heuristic pi tilde. Then from that you solve this rollout algorithm, you get the second base heuristic, so pi tilde 2. Then you do the optimization again, you compute this v tilde, and then you do this optimization again, then you get the third base heuristic, then again you compute this v tilde, then again you solve this problem using rollout algorithm and you get the fourth base heuristic, and you keep doing it again and again, And eventually, the sequence of policies converges to the optimal policy, the truly optimal policy in the case of reinforcement learning. So I'll be teaching a course in reinforcement learning next year. So this is an advertisement for my course next academic year, not next year, but next academic year. So this is just an advertisement for my course 2 years down the line, or maybe 1.5 years down the line. Okay. We ourselves have used rollout algorithm for multiple problems. So one of the problems we solved was charging of electric vehicles, a very complicated problem. So the problem, this was done in collaboration with Ford Motor Company. Our state space was 500 dimensional. Our action space was 200 dimensional. That was the easy case, by the way. The full-blown case would be like 2000 dimensional and 500 dimensional, but we didn't solve that problem because we didn't have the compute with us. So 500 dimensional state space, 200 dimensional action space. We needed to solve this problem, and we basically came up with some sort of base heuristic using a complicated, time-consuming reinforcement learning problem. By solving that reinforcement learning problem, we got this base heuristic. And then after that, we used this rollout algorithm in real time to schedule the charging of electric vehicles. So we started with this problem, very complicated. We spent 3 hours trying to come up with the base heuristic, and then within 15 minutes we were able to solve this. We were able to solve this problem and get the charging schedule of electric vehicles. Then in another problem, the problem was to figure out how the velocity of the vehicle should change in order to minimize the total cost of fuel. So this was also very similar to the rocket problem that I was talking about. But the issue was that at every point of time, this constraint is going to change because the vehicles that are around you will either come into your lane or move out of your lane. So in fact, at the very beginning, I don't even know what all vehicles I'm going to see and what all constraints I'm going to see on the road. Okay, so the way we came up with this base heuristic was a policy constructed by assuming that there is no traffic on the road. How will you drive if all the traffic lights were red light and if there was no cars on the road, right? So we came up with a base heuristic policy from that, and then we solved this rollout algorithm using the base heuristic policy with the traffic. So then we introduced all these constraints afterwards based on the real-time information of the traffic. Okay, so when in the beginning for the computation of base heuristic, I didn't assume this constraint, and then after computing v tilde, we introduced this constraint based on real-time information and solved this problem and came up with a way to make sure that the total fuel consumption of the vehicle is minimized. And both these algorithms, we filed a patent for it, like OSU filed a patent for it, and it's still pending at this point of time. So this is a very, very, very sophisticated algorithm. I wouldn't, the idea is very simple, but it actually can give you a lot of benefit in a lot of different situations. So this algorithm is used heavily in process control. This algorithm is used heavily in all the AI/high dimensional optimization problems. Any questions? As far as the optimality property goes, model predictive control is as good as this state that you are tracking. Okay, so you will have some loss. If this is a very good estimate of what the state should be, what the state trajectory should be, you will have a very small loss with model predictive control. But if this is very off, then you will have a pretty bad loss here. In rollout algorithm, if you have a very good base heuristic, your optimal solution, so whatever pi hat star you get, is strictly better than the cost that is achieved using the base heuristic. So that's roughly the theorem, which is this policy is strictly better than this policy in terms of the total cost incurred.
And how quickly you converge is dependent on the base base heuristic chosen?
Kind of, yeah. So in the case of the second example that I talked about, where we were trying to minimize the fuel consumption of autonomous vehicle, the base heuristic took us 1 minute to compute, and then after that we can compute this problem. We can solve this problem in real time within like 100 or so milliseconds in the vehicle. Okay. In the case of EV charging problem, remember it was a very complicated problem with much higher dimensional state space and stuff. So the base heuristic took us 3 to 4 hours to compute using some reinforcement learning algorithm, and then executing this took us 15 minutes, which is for scheduling the charging of electric vehicles, that would be considered near real time, because vehicles are arriving in the span of minutes and 10-15 minutes interval, so it's kind of near real time for the vehicle's case. Any other question? Okay. I hope somebody will ask me a question, and so I don't have to start a new topic, but now you are forcing me to start a new topic because we still have 15 more minutes in this class. Okay.
You can also
The University Ethics Committee doesn't allow me to end the class before 1:35. Okay, so the next topic that I wanted to talk about is what is called as function approximation theorem. Okay, so one of the problems we have encountered time and again in the context of dynamic programming is we need to store this function. Okay, we need to store it in the memory of a computer. I need to store this function in the memory. Okay, so there are all these functions that I need to store. So what are the two functions that I need to store? One is my Vt that maps xt to r, and the other one is pi t that maps xt to ut. So you can think of this as Rn and this as Rm. And I need to store a function. F is already used, right? I need a symbol for function, arbitrary function. F, G, H. E. Have we used E? We have not used E. No, E was a vector. It doesn't matter. I'm going to use F. So I need to store a function F from Rn to Rm. I have samples xi, f of xi. I equals 1 to capital N. So I have capital N samples of xi and f of xi. And from this data set, I need to map it to a function f hat that is very close to this function f. Okay, that's our problem statement. So do you all see why we need to solve this problem? So everywhere we need to store a policy and we need to store a value function. So we need to store a function in the computer's memory. Depending on the hardware, sometimes you need simple functions, sometimes you need complicated functions. So when I'm talking about driving a vehicle and I'm computing all of the stuff on a microcontroller, then I can't really have a very complicated function class that I can store in the memory. On the other hand, when I'm solving this EV charging problem, I can actually have very complicated function approximation because I have like the entire supercomputer in front of me to use. Okay. Now the question is, what would be a simple way to store this value? So I have xi and I have the value. So this is in Rn, this is in Rm. How do I store this Rn, Rm pairs as a function? What's the simplest function you can think of? So let's say the simplest function is theta transpose x. Right? So theta is Rm cross n. That's the simplest function. How do I get the value of theta? What will you do? So I give you this data set of Rn, Rm pairs. These are n points, capital N number of points. And let's say we just want to stick to linear function approximation because I'm doing it on a microcontroller and my microcontroller cannot handle more sophisticated function approximators. So how do we compute this theta? Yes?
Linear regression.
Linear regression. Right? So we can solve this least square problem. So theta transpose xi minus f of xi L2 norm square summation I equals 1 to n 1 over n. We learned how to solve this problem in like lecture 6 or 7, right? Least square, how to solve the least square problem. So that's how we will solve this problem. We'll minimize this over theta. And then I can get theta star, and that will be my function approximator. Okay. Anything else that comes to your mind? What's the next complicated function approximator? Sorry? Quadratic? Yeah, I think certainly quadratic can also work. So f hat of x is x transpose qx plus b transpose x, and then I can try to do the same thing and I can minimize over all q and b, and I can get appropriate value of f hat. This is going to be a bit more complicated than this. Computation of this is going to be a bit more complicated than this. So you need a bigger microcontroller to solve this problem. What else? What's the next in line? Yeah.
So, I mean, the linear regression is like a maximum likelihood estimation. So maybe if you had some assumptions, you could say it's a maximum a priori estimation problem.
Yeah, but those are typically done for probability distribution. So we are not really doing probability distributions here.
So
We are doing general functions.
Okay.
Whenever you are talking about that, then these are generally like a Gaussian function or something like that. So we are not doing any of that right now. So what's the next complicated function? Yes?
So this line of interpolation goes through the origin. So if we add a constant and
Sure, yeah, you can add plus c here or plus b here. Yeah, you can do that. Anything else?
can we use neural network?
We'll get to neural network in a bit. I want to go step by step. Yeah.
I think
Neural network? Okay. Yeah, so we can do polynomial. So we can do f hat x equals to summation of aij xi xj and whatever ij equals 1 to n plus bij But this is only giving me an R, so I can do like multiple such functions. So let me call this K. And then I can stack these f hat K so as to get this Rm dimensional object. So I can do these polynomials, and you can put any exponent here, I don't know, alpha 1, alpha 2, and you can try to optimize over aijk and bijk, right? So polynomials are the next complicated function approximators. Then we want it to be a bit more complicated. Then we can get to neural networks, which we have already talked about how to approximate neural network, train a neural network. Then if you want to be more complicated, you can do convolutional neural network, and then you can have transformers. So these are the things that people generally know. There are other function approximators as well, such as support vector machines, decision/regression tree, random forest, reproducing kernel, Hilbert space, and then what else? I think that's pretty much it. There are a lot of such function approximating classes. Each of them have their own benefits and there are some more actually. Let's talk about it in a bit. Okay, so there are some more function approximating classes. K nearest neighbors. Then you have spline, and then we have kernel based. This kernel and this kernel are two different kernels, so don't mix up the two kernels. Okay. So what you see on the board is a jungle of function approximating classes that people have tried for various applications. So let's get into this. So where exactly do we use all of these function approximating classes? So what I'm going to do in the next class, let me give you a preview of what we are going to do in the next class. We'll talk about different classes of function approximating classes. So specifically, these are all parametric function approximators. These are non-parametric function approximators. Decision tree and random forest, these function approximating classes can approximate discontinuous functions. Neural network, convolutional network, transformers, these can approximate support vector machine and reproducing kernel Hilbert space. These function approximators can approximate continuous functions. Okay, so if you have like a step function can be approximated using a decision tree, but it can never be approximated very well using a neural network, okay, because it's not continuous. So what we are going to do in the next class is we are going to talk about what each of these function approximating classes do, what are the benefits, what are the drawbacks of the function approximating classes. This one is a randomized function approximating class. There is also a random kitchen sink. So this is a random function approximating class. These are discontinuous function approximating class. Then we have the regular continuous function approximating class. So we'll study the properties of this, and we'll talk about for a given problem, how do you pick what the right function approximating class is going to be, both for the policy function as well as for the value function? I think one of the things that people tend to not think more when you look at the literature on reinforcement learning and when you look at the literature for approximate dynamic programming, pretty much everyone just sticks to neural network and doesn't move beyond neural network. But the only case I'm going to make in next class is that there are other function approximating classes as well, and that depending on the application, depending on the hardware, depending on the computational complexity, you can pick one of these different function approximating classes so that you are not stuck to neural network for all your life. Okay, so we'll do that in the next class. We'll talk about various function approximation theorems. That will happen for the next 2 classes actually, and then we'll connect it to cost function approximation, model approximation, policy approximation, and value approximation. So these are the 4 different approximation techniques in approximate dynamic programming. Then the base for all those 4 approximation techniques is basically the function approximation theorem. So that's why we'll talk about function approximation theorem, go back to approximate dynamic programming, connect it to approximate dynamic programming. And then next Monday is going to be our last class for the semester, because I'll be out of office the week after Thanksgiving. Wonderful. So I stopped this class right on time. So thank you so much for your patience. See you on Wednesday.